So, okay, welcome to lecture 13, stability of structure. So, let us briefly recapitulate what we are discussing. We are discussing the buckling of plate buckling, right? And before buckling, we reviewed briefly the theory of plate bending. We have reviewed the theory of plate bending, and then we have derived the equation, governing equation for the plate bending. The theory of plate bending was, we made some assumption of, plate bending, and the plate bending that we are considering is Kirchhoff's plate bending theory. So, here it is thin plate bending. We are assuming that the plate is thin plate bending, and then there are a certain assumption, and the main assumption is that, of course, thin plate means, its depth over the, length over depth ratio is much greater than 10, okay, and 8 to 10 whatever, okay, it's not very, sacrosanct number though. And then plane section remain plane after bending, right, all these assumptions. And then we have, introduced, we have reviewed, there are two approaches. One, directly we can start with the equilibrium equation, right, from, what we have learned from the continuum mechanics, or we can, and then, so the first approach that we consider the sigma ij comma j is equal to 0, of course, in absence of body force, and then in absence of inertia, and then this will give three equilibrium equation. So, now if you consider Cartesian coordinate system, we integrate this, these are the equilibrium equation in terms of stress tensor, right. So, if you integrate this over thickness, okay, along z direction, over thickness, directly equilibrium equation of, you integrate over thickness, then you will get the equilibrium equation, where you will relate the, shear forces with the externally applied load, right. And then you multiply the equation with thickness, with the z, that means the thickness coordinate, and then you integrate for the equilibrium along x and z, okay. So, there are three equilibrium equations, one equilibrium equation along z direction, another equilibrium equation along x, another equilibrium equation along y. So, along z direction, that is what you integrate over the thickness, that will give you the equilibrium in terms of shear externally. Now, the other two equilibrium equation in x and y direction, you have to multiply those things with thickness direction z, and then you integrate over the thickness, that will give you two equations where the bending moment and then the twisting moment is related to shear forces, right. Then three equilibrium equation you combine everything expressed in terms of bending moment and twisting moment. Then you decide, consider the kinematic of deformation, or you relate bending moment in terms of the, texture, rigidity of plate, and then the curvature of the plate. So, of course, here will be direct curvature del w del x2, but cross curvature del 2 w del x del y, because twisting moment is there, right. So, there will be three, moment curvature relationship, two are for direct bending moment, another one of the twisting moment, okay. And then everything, if you, on combining everything, you are getting the governing equation lambda square, w x y is equal to q x y, and then there was something d, okay, and d is the flexure rigidity for the plate. So, E T Q divided by 12 into 1 minus nu square, nu is the Poisson ratio, W is the vertical deflection, right, and Q x y is the external loading, right, and the choice of coordinate, that is what we have made, is x, y and z, right. Now, this we can directly derive from there, or what we have considered, I have also shown in the previous lecture, that you can directly consider a differential element, dx d, okay, and then you can, write down the bending moment, bending moment, and then a, twisting moment, and then the bonding moment, bending moment, okay, and then the shear force, and then you directly, of course, these are the bending moment, twisting moment per unit length of the plate, right, and then you can directly write down the equilibrium equation, moment equation, and then you can arrive at the same governing equation, right. So, that basically we have reviewed the theory of plate bending, okay, Kirchhoff and thin plate bending, right. So, now what this must have been, and then it will be accompanied by the boundary conditions, right. You can see this is the fourth order equation, governing equation, right, partial differential equation, linear, and then you require 4 boundary conditions, right. So, in each side 2 boundary conditions, okay. Now, if you want to do plate bending, then what additional thing you required? So, the additional thing that is required for the buckling of plate is nothing is that, two way you can do, for plate buckling, plate buckling. First thing, you have to consider the equilibrium in the deformed configuration. Here, we didn't consider the equilibrium in the deformed configuration, we have considered the equilibrium in the configuration, okay, without deflection, right. So, the first assumption that we are going to make in the theory of plate buckling is that this equation, and then for buckling we do not care about the external loading Qxy, right. So, we have considered, let us consider the part, this one, the first part. This is the flexure rigidity of the plate per unit length, right. Now, you may wonder that why this equation is not changing, because we will have to consider the equilibrium in the deformed configuration, right. So, what we are considering the equilibrium of the plate, it is something like this, x, y, z, something like that, right. But what we are supposed to do, we must consider the equilibrium in the this configuration, right, deformed configuration, right, something like this. You see that? Maybe here is the x, here is y, and here is z, okay. Of course, here you do not essence, something like this, and then here also it will be something like this, it will be something like this, right. So, there will be some deformation, right. What assumption we are going to make is that in undeformed configuration, from undeformed to deformed configuration, okay, what will happen, because it is deformed, when you are considering the equilibrium in terms of shear force or bending moment, okay, it might be that there is a extra component that might come due to additional curvature that is coming, but we are considering that as far as these equations, this part of the equation is concerned, this part of the equation is basically in terms of shear forces, vertical shear, out of plane, not in out of plane shear, right, shear forces, and whatever the bending moment, those does not really change significantly because of this deformed configuration. From the deformed, so as far as this equation is concerned, we do not distinguish between the deformed and undeformed configuration. You understand what I am trying to? This equation may change little bit by considering this deformed configuration of the plate, because there will be little slope here, okay. And so, earlier this was the shear force Qx, right. Because there is little slope, there might be some vertical component when you are considering, there will be some component Qx into something like del W dl, something like that, okay. But that we are not considering, we are considering those contributions are negligible. You understand that? Now, however, we cannot do it so, because buckling also essentially requires that you need to have in plane forces, right. So, what we are considering here is basically the equilibrium of the out of plane forces. This basically considers what? The equilibrium, force equilibrium along z direction and moment equilibrium along x and y. This is the consequence of these three equations, but we do not consider the in plane forces here, right. We have to consider in plane or compressive forces here, right. So, let us keep it, and then what we are considering, that let us consider now in plane forces, and you see the component of the in plane forces that is contributing in this equation because of this deformed configuration, only that part we are going to consider. So, for that let us see what we are going to do, okay. So, we are assuming, so this we are considering the plate, this is the plate in the, but its deformed configuration, and what you can see, the influent forces you can consider, influent forces, please draw it, are Nx, Ny and Nxy. Please note that Nxy and Yx are same. And as of now, we have assumed that these are tensile forces, but later sign will automatically come. So now, this is Nx, this is Ny, and this is Nxy, okay. Nxy and Yx are complementary, that's why all of the influent forces, and we are considering deformed configurations. So what do we want to do really? We want to see that how, because of the deformation, because of the perturbed configuration, as required in stability analysis, we want to see that how these in-plane forces are going to contribute in the vertical equilibrium. Essentially, this equation is nothing but this is a vertical equilibrium equation in z direction, right? The origin of this equation is what? Equilibrium along z direction, right? Equilibrium along z. Equilibrium along z. That is the first equation, right? And then of course we have really, so we want to see how these in-plane forces are affecting the equilibrium along z, okay. So the component of in-plane forces, along z direction. Okay, so what are the component? Nx, and if what you see that we are assuming Nx, Ny and Nxy to be constant over the plate. There is no variation. You see, so Nxy, Nx there is same. So it is subjected to constant force, constant axial force, membrane force. Okay. So what is this? Will come downward, right? Nx del W, and because it is a small deformation, cosine of this thing will be cosine of this will be sine of this will be nothing than this one, right? So Nx del W del x plus del x del W del x dx, right? And this one, this will come downward, this will come upward. So this is minus del W del x, right? Similarly, for Ny, what you are going to get? Ny, look, this is Ny, right? Ny. So this, vertical component downward, this one, it is del W del y plus del y del W del y dy minus del W del y right. And of course, if you want to consider for Nx, this we are considering a very small element of length dx and dy. So this distance is dy. So I want to multiply with dy, right? Dy, okay? Dy. Component influent forces, right? So dx, this similarly here we should multiply it with dx, right? Dx, right? Then what are additional stuff? Plus here plus Nxy. What about Nxy? This is Nxy. It is downward. What is that? Del W del y. Del W del y plus del x of del W del y dy, right? And then minus this one is what? Del W del y, right? Nxy del W del y. And this is into dx, right, plus Nxy now you consider this one. So del W del x plus del y del w del x dy minus nxy and then del w del x del x and dx. So, these are all plus sign. You see that this is for nx, this is for ny, this is nxy, this is nxy, right? All of you understood how from where this expression is coming, right? Huh? Okay. Then we are considering this force and its component along z direction, right? And then from both sides, that's what within one expression we are basically subtracting the component for negative x, negative y, and these things. So, if we simplify this will go, this and this will go, this and this will go, this and this will go. So, ultimately what we are going to get is here you see that nx del 2w del x2 plus ny del 2w del y2 plus 2 in xy del 2w del x del y dx dy, right. So, over this small segment, small plate segment in the deformed configuration, because of this deformed configuration, if we consider the contribution of the in-plane forces along in the vertical equilibrium, then we got these forces, right. Now, for per unit, now for per unit length, so the component of in-plane forces along positive z direction per unit length. This is for the dx dy element. So, per unit length will be what? Nx, you just divide it dx dy, right? So, nx del 2w del x2 plus 2nxy del 2w del x del y plus ny del 2w del y2, right. Now, so you understand that? So, this must contribute to this equation. So, in the right hand side, so these are nothing but vertical equilibrium. So, in the right hand side, we will add this term. So, this basically is going to be nx d2w dx2 plus ny d2w dy2 plus 2nxy d2w dx dy, right. So, I am removing all other things, right, all other things. But please note that this is a very important to note that because of this deformed configuration, if we would have considered this shear forces qx, qy, okay, they will also have little inclination and that component will contribute in that vertically, but that higher order contribution they were neglecting. But for the in-plane forces, for the out of plane, say, because of the deformed configuration, the contribution of the out of plane forces in the vertical equilibrium we neglect, but the contribution of the in-plane forces in the out of plane equilibrium equation we are accommodating, right. So, that is basically the governing equation now, understand. So, of course, this is one way, all of you have noted down all the, right. See, the thing is that, well, here once again we did it in an ad hoc, a quark way, where we are considering a small element, and we are trying to, find out the component. Well, I mean, this is one way to derive the equation, but if you want to do it smartly more, then what will you do? Is there a smarter way to do this, to derive the equation, this equation? Yes, why not? How will you do that? Could you please, do you have a clue? Huh? How? Now, the way we did it, we are considering now these equations, the way we have derived here, we always consider a small element and then we enforce this thing, right? But we never, the way I mentioned to you that just by integrating this, you can get this part of equation, right? How will you get this equation? This is a smarter way to do it. Directly from continuum mechanics, you will get this equation, right? At least from this equation, you will get this part, right? But how will you get this part? This is much smarter derivation and you don't require to care about anything. Just start from a very basic Cauchy, equilibrium equation, equilibrium equation, then you integrate. This is sufficient for this, but how will you do this? See, Cauchy stress tensor doesn't distinguish between the deformed and undeformed configuration, right? From this equation, you will get this part we will never get. Because how the sigma ij is defined, Cauchy stress tensor? Sigma ij is defined in the, where both the, sigma ij is what? Force per unit length, right? Both the force and the area, reference area, both are in the deformed configuration. We have learned, right, Eulerian and Lagrangian, right? Total Lagrangian, updated Lagrangian, those. Huh? We have to consider alternate stress measure. Okay. So, alternate stress measure, which stress measure should we consider for equilibrium equation, where the force may be in, of course, always in deformed, but then the area is in undeformed configuration, because then it will distinguish between the two. Of course, we will see this equation is nothing but what? The divergence of stress tensor is 0. So, we will instead, divergence of first Piola-Kirchhoff stress tensor to be 0. First Piola-Kirchhoff stress tensor, divergence of first Piola-Kirchhoff stress tensor. First Piola-Kirchhoff stress tensor is what? First Piola-Kirchhoff stress tensor defined. It is a 3-dimensional generalization of the. You have done this uniaxial, tensile testing in your second year strength of material class, right? And then can you recall that you have plotted the plot, you have plotted two graphs, right? One was like this and then coming down, but another one, this plot, can you recall? So, the first one was sigma was what? Sigma, this one P by A, this one is P by capital A. That means you can recall that this was your tensile specimen, right? Here, if force P is always there, right? But if you consider the area, look, when you are considering the area, when it is expanding, the area is also contracting because of Poisson's effect, right? So, area is also changing. If you consider that, so the changing, the reduction in the diameter, that is the area is changing. So, if you consider the changing area, then you will get there is rising curve. But if you do not consider that nominal, then you will always get like this. Now, this is the 1-dimensional. If you generalize this in 3 dimensions, this is the Cauchy stress tensor. If you generalize it, This is the Piola-Kirchhoff first Piola-Kirchhoff stress tensor. Okay. So the problem with Piola-Kirchhoff stress tensor is that Piola-Kirchhoff stress tensor, I don't know. This is the equilibrium equation, but momentum equation, there is a problem, because what happened is that Piola-Kirchhoff stress tensor is not symmetric. That means P is not first Piola-Kirchhoff stress tensor, it's not P symmetric. So what happened is that although this is linear momentum balance is linear, but then the angular momentum balance is non-linear equation, okay, because it is not symmetric, okay. So that's why we define the second Piola-Kirchhoff stress tensor as second Piola-Kirchhoff stress tensor is. So this is the first Piola-Kirchhoff stress tensor, first Piola-Kirchhoff, and this is the second Piola-Kirchhoff stress tensor, and F is the deformation gradient. So then it will be divergence F equal to 0. F is the deformation gradient, okay. So now with that, so earlier this is nothing but linear momentum balance. Linear momentum balance for the first Piola-Kirchhoff stress tensor was linear, but as soon as you are doing it in terms of second Piola-Kirchhoff stress tensor, it become non-linear because it is a product of two terms, right. However, the beauty is that although the angular momentum, the linear momentum balance is non-linear, but the angular momentum balance will regain the S symmetry. That means S is equal to S trans. That's the beauty of the second Piola-Kirchhoff stress tensor. That's why second Piola-Kirchhoff stress tensor was introduced. You see that? I don't care about this, but yes, I care about this. I will show you from here how it is coming. So let us work with second Piola-Kirchhoff stress tensor, and the beauty is that unlike Cauchy stress tensor, second Piola-Kirchhoff stress tensor will allow you write. Now I will write it in terms of indicial notation. Indicial notation, right? This repeated index ij, this is now. Please note that capital this is undeformed configuration and small is deformed configuration, okay. You must understand that deformation gradient is a 2-point tensor, because deformation gradient is what? Deformation. So it is one leg is in one leg is undeformed configuration, another leg is in deformed configuration. So it's a 2-point tensor, right? And what is Fij? What is Fij? Fjk is nothing but what? Fjk is nothing but deformation gradient is nothing but what? Dxj, d capital Xk and Xk dx j plus u j dxk, and this is dx j d capital. You express displacement gradient in deformation gradient uj by xk. This is nothing but Kronecker delta jk, and this is nothing but duj dxk. So then you substitute it over here. So when you substitute, here, so S ik and Fjk is nothing but delta jk plus uj xk simplify it. Sik delta jk will be, k is repeated index, so k will be dropped, right? So it will be Sij plus Sik uj. All of you are conversant with conversant with this, conversant with what? Indicial notation, right? All of you, right? We are assuming that the plate is subjected to uniform forces, right? So, I can neglect it variation over xk. So, I can take this thing out, ik, and what I can write del 2 u j divided by del xi del xk is equal to 0. Now, now I will explain to you. This second Piola-Kirchhoff stress tensor, this is nothing but what? This is nothing but Sij, comma I plus Sik so this one, if you don't consider this, this one gives you this part and this one gives you this part. Do you see that? Sij, nx, nxy, nxy and del 2 uk del x del ij is del 2 w del x2 del 2 w del x. Do you see that how? So, if you integrate once again, if you integrate over thickness direction, that will give you the vertical equilibrium equation, force equilibrium, and then you integrate this, you multiply that with z and then you integrate it over thickness. Then you will get two moment equilibrium and then ultimately you will get this thing. So, this is much smarter way to derive this directly from continuum equation. So, whatever I have done is a little ad hoc way to derive this term, but nevertheless that is more physically relevant, at least because we can physically understand what the hell going on, right. So, I prefer to derive this thing using the previous approach. Nevertheless, I would like to corroborate it with whatever we have learned in our continuum mechanics using the second Piola-Kirchhoff stress tensor, which allows us to distinguish between deformed and undeformed configuration, and hence we get the additional gradient term that must be accompanied with the in-plane forces to have their component in the z direction. Clear? All of you have noted down this. So, this equation will allow us to study stability, okay, of a plate, right, or buckling of plate. For the time being, we are assuming that nx, ny and nxy does not change along the length of the plate. They are constant, right, first thing. So, this is a boundary, this will lead to eigenvalue problem. This is the governing equation, it must be accompanied by sets of boundary conditions, right, that we will see. The first problem that we are going to consider is buckling, uniaxial buckling of a plate, of a rectangular plate, okay. Along x A, along y B. length A and B, okay, and I am assuming this is simply supported, or these are simply supported. These are all simply supported. Simply supported means you can understand that. Now, these are all simply supported, okay. Simply supported means something like this. But please note one thing: these are all simply supported, huh? But please note one thing. See, in order to allow it for buckling it, we must allow axial deformation, right. So, they are simply supported means they are restraining out of plane deformation, but not the in plane deformation, because you have to allow the thing to get compressed, right. So, it will not restrain the in plane things, okay. That means it must be something like roller here, okay, roller, huh? Understand that, right? Okay, good. So, then what are the boundary conditions? If the simply supported, what are the boundary conditions? So, if you require simply supported means two boundary condition here, two boundary condition there, all edges two boundary conditions. So, at x is equal to 0, at x is equal to a, at x is equal to 0, of course, w 0, w 0, and right, and what else? Of course, yeah, all the edges basically at y is equal to 0 and y is equal to b, w must be 0, w must be 0, right. What else? Another thing is that we are considering bending moment along x direction, that means mx. Mx must also be 0, mx must be 0, right, and mx is what? Minus d d2w dx2 plus nu d2w dy2 must be 0. Now, at x is equal to a 0 and at x is equal to a mx. Now, here bending moment, here bending moment, okay, this bending moment, huh? Right, huh? Right, bending. So, you see that this is anyway supported along y. So, deflection is 0 all along y. So, there cannot be any variation along y. So, d2w dy2 is anyway 0, right. So, what does it mean? That means this implies that del 2w del x2 must be 0. So, along with w is equal to 0, in both the cases del 2w del x2 must be 0 and del 2w del x2 must be 0, and similarly here also, here my should be 0. For that, here it will del 2w del y2 must be 0, along y is equal to be del 2w del y2 must be 0. Understand, right? So, the boundary conditions is that x, here once again if you want to write at x is equal to 0, is equal to a, w is equal to 0, del 2w del x2 is equal to 0, at x is equal to y is equal to 0, y is equal to b, w is equal to 0, del 2w del y2 is equal to 0. Fine? Okay. So, now, and then of course, because it is only axially loaded, all other things are not there, right. Nx d2w dx2, right. So, what we will do that can we have some expression which will allow this, you have solved the plate equation, right, Navier's approach, right. Can we use the same approach here using double Fourier series? Yes. Can we assume some function that will satisfy the boundary condition? So, how we can so let us assume wx comma y summation of a mn sin m pi x upon a sin n pi y on b, where this is double summation, right, m is equal to 1 to infinity, n is equal to 1 infinity mn, right. M1, 2, 3, N1, 2, 3, double Fourier series. If let's see that whether it really satisfies x is equal to 0, yeah, it will be 0. If you take double derivative, then it will be sine will be cosine will be sine once again, and then all these boundary conditions are satisfied, right? So that basically satisfies the boundary condition. Now, so you substitute in the equation that assume you substituting in this equation, substituting this expansion expression here. So what you will get? See this, if you differentiate, the way you are going to get del 4 w del x4 plus 2 del 4 w del x2 del y2 plus del 4 w del y4 is equal to nx del 2 w, right? So you will see that here, d. So you differentiate it with respect to of course 4 times. So m pi by a to the power 4, right? And then 2 m pi a square, and then n pi by b square, and then n pi by b over 4 a m n is equal to nx d2w dx2 will be of course a m n m pi by a square. Okay. Both sides sin m pi x by a, sin n pi y by b, you can cancel out both sides, right? And then of course a will also cancel out, right? So then what we are going to get is from there, from here you see here, I think here there will be negative sign, right? Because isn't it? Nxy will be minus d a by m pi square down this one, right? This negative sign is coming because we initially assume tension, but it is compression, right? That's why, then minus d, I will just see the simplification, in what format they presented, okay. So this pi square, if you, the one pi square will remain, so minus pi square d by, if I take b square out, then it will be mb by a plus n square a by MB square. Okay, that this kind of expression it will come. Okay, I don't know how this is. Please check. So of course negative is because it is compression. This is for compression. Now we will do little simplification. What kind of simplification we are going to do? So we'll assume that, well, let us have the plate in which the plate, we are assuming, we'll assume that this plate along x direction it has whatever, but along y direction it will buckle in single buckle, right? So that's what I am assuming, that's what I am assuming, this something like this, something like this. So when I am assuming this expression sin m pi x upon a sin n pi y upon b, this n pi y being n is equal to 1, because when it is buckle in on y direction, if it is buckle on a single buckle, then it is 1. So here n is basically 1. So sin n pi y upon b is basically always we are taking as sin pi y upon b. You see that? So for this, so the simplification is that along x direction we are not constraining, but along y direction we are constraining, that it is buckling in single buckle. So we are basically essentially converting the problem, instead of dealing with 2 dimensions, we are dealing with only 1 dimension. What is happening in? Let us see, and that will even reveal many important conclusions, right? So nxy will be, in that case, will be minus pi square d upon b square, and then mb by a plus n is of course 1. So a by mb square. Okay. So this is the n critical, considering this thing. This is the critical load. So minus pi square d upon b square mb by a plus a by b square. Now we will even see some other things over here. Okay. See how we will try to minimize n critical with respect to m. So treating, of course, m is an integer, right? So treating, so if we minimize n critical with respect to m, let us see what happens. Okay. So for minimization, for minimizing, for minimizing n critical with respect to m, right? So then dn critical by dm must be equal to 0, and then when you differentiate, you see that what you are going to get is that mb by a is nothing, m is b by a. Well, I mean, so 2 mb by a plus a by mb, and there is a m is basically b by a, and minus a by b m square equal to 0, right? So this cannot be. So here, from here, what we get, that b by a is equal to a by b m square. That means m square is equal to a by b square. So m must be equal to a by b. That means, what does it mean? This means that the critical load will attain minimum when this a and b will occur, a by b is basically, appears in a multiple, okay, or integer multiple. That means its aspect ratio is an integer. You understand? So for critical, that means that is, integer aspect ratio, So this is the condition of the minimum integer aspect ratio for critical load to be minimum, okay, minimum. And what is the value, minimum value? The minimum value is, you see, substitute NCR is equal to, you know, pi square d by b square, and then m m is equal to a by b, you know. So m is equal to a by b, right? A by b into b by a by b, and 1 by m means b by a. So this is 1 plus 1 square, so that means, you know, 4 pi square d upon b square. You see that? So the critical load depends on the aspect ratio b, you know, dimension over the other direction, smaller direction, right, b. And because what we can see that m is equal to a by b, that condition we have obtained. So when the aspect ratio of the, you know, plate is integer, then the critical load is 4 pi square d by b square. Okay, it depends only on b, the smaller dimension. Okay. Now what happens if it is not minimum? Then what happens? Of course, then n critical is pi square db square mb by a plus n. Now what we see? That another thing I would like to put here. So if you plot the n critical over a by b, you know, here you n critical and here you can put a by b. So here is 2, here is 3, 4, 6, okay. So here it is 4, okay, 4, 4. So that's what 4 pi square d by b square, 4 pi square d by b square, okay. So, you know, here what will happen? Here it will be see between 1 and 2, and this will be root 2 between 2 and 3, this one corresponds to, you know, root 6, and this one corresponds to root 12, root 9, you know, root 9, and then in here it will correspond to root 12, something like that. So what happened is that you see, see this is the, I am plotting that n here divided by, you know, pi square d by b square. So this is always 4, right? So what happened? First this is buckling. So as the aspect ratio is 1, then if A is equal to b, the minimum is attaining, right? In either side, when the aspect ratio is not 1, not integer, both sides, whether it is decreasing, increasing, it will increase. And then when it is coming to some point, you know, then if it is crossing root 2, if it is slightly less than root 2, then of course it will buckle only with, you know, the first mode, m is equal to 1. So this is m is equal to 1, this m is equal to 2, this is m is equal to 3, m is equal to 4. Then as soon as it crosses root 2 aspect ratio, then it will buckle, there will be 2 buckle, because from here there is a shifting in mode transition. Then it will remain this, of course critical load will reduce when it is in perfect integer this, then once again it will rise, then once again there is a mode shifting at root 6, and this root 2, root 6, you know how you can obtain this thing, let me show it. So nx m is equal to nx m plus 1, does mean the critical load at m mode and critical load at m plus 1 mode should be same at this point, right, or this point, right. So here you can clearly see that the m b by a plus a by m b is equal to m plus a b by a plus a by m 1 into b, right. And on simplifying on simplifying, you know, a by b will be root m into m plus 1. Huh? Oh, it will be root 12, sorry, root 12, yes, root 12, yes. So you please see here. So from 1 and 2, so root 1 into 1 plus 1, then root 2, okay. Here root 2 into 3, that means root 3. Here root 3 into 4, 12. Then here root 4 into 5, root 20, okay. Here it will be root 20, okay. Something like that, okay. Why this is happening? Because you see, when this, you know, the plate is able to buckle in perfect square shape, or in a shape in which, you know, that a and b occurs in integer, right, that is being energetically favorable over other. You see that? Because that basically that is conducive to perfect buckling mode, that is what we assumed, right. Sin m pi x by a, sin n pi y x by b, okay. So you know, perfect sine curve is possible only when they a and b appears as integer, that is what is essentially happening. So that is what aspect ratio 1 it attains minimum, aspect ratio 2 3, of course when the aspect ratio 2, then there will be 2 buckle along, m is what, m is number of buckle along x direction. So then minimum will attain when the number of buckle is 2, because it is buckling in second mode. Then in aspect ratio third, the buckling, you know, the mode which is giving minimum is of course the buckling mode, you know, third buckling mode, which is 3, you know, wave number, right? I mean 3, you know, you know, the half period functions, right, and then similarly 4. And from there is a point of transition where the mode transition is occurring from mode 1 to mode 2, that basic, or mode 2 to mode 3 happens when a by b is root m plus 1, okay. So you see that, so this is nothing but m and n by b is same, okay, this, okay, fine. Now it's not that, so these places, you know, this looks like what, this looks like what, this is look like tongue, na, right. This is called Arnold tongue, you can call it Ma Kali's tongue, okay. If you don't want to call it Arnold. Why it is called Arnold tongue? Because Arnold is the scientist, he basically, you know, studying some problem. This thing is not common here. I mean, if you want to study stability domain, there are many cases appears, not only in elastic stability, but in hydrodynamic stability, in magnetoelastic stability. I have seen some recent, you know, research paper appearing in PRL, where this Arnold tongue they are you know, demonstrating on quantum optic. There is some phenomena having quantum optical phenomena. So they did some experiments. So how this Arnold's tongue is showing in the, you know, parameter space. So how it is experimentally, how they are showing the disparity between the experimental and then the theoretical one. You see those, this looked strung like structures called Arnold strung. Okay. So, what we see that and how it will buckle, even you can clearly understand that. Well, I mean, if you have having like this kind of things, and then it is having perfect ratio 3, right. So, on this direction it is always like that, always like that, always like that, right. In other direction it will be something like this, it will go and then it will something like this, is there. So, you see, so there are 3 complete web, okay, 3 web number, okay, here is single web number, because a priori we have assumed for simplification that the plate will buckle only in single mode because other direction we are assuming to be much smaller. B, A is, we are assuming A is the higher dimension, much smaller than. So, along the shorter direction we are assuming that the single mode prevail, okay, and the other direction basically the minimum theoretical load is attained when the it is appearing in perfect integer, and that is what we can see. So, this is for the uniaxial buckling. You can also study the biaxial buckling. Of course, things will be little more complicated, but but that and you have to plot the stability diagram. Here it is only one controlling parameter, okay. So, M or A by B, but there it will have more, and then instead of N, so if you just write the governing equation, nabla square W x comma y is equal to Nx d2 W dx2 plus 2N xy d2 W dx dy and plus Ny d2 W dy2. So, if you want to study, now I am considering all other things as 0. You can consider Nx and Ny. So, a plate you consider the biaxially loaded plate. So, a plate simply supported maybe, and it is biaxially loaded, okay. The aspect ratio A by B. So, biaxially loaded plate. Of course, then you have to consider combination of Nx and Ny, Nx and Ny, and then if you want to study the stability, then you have to plot everything when it is buckling or not, a different combination of Nx and Ny, and there you can distinguish what is the stable and unstable domain, okay. But you can always consider there is some ratio, maybe some ratio R is equal to Nx by Ny, and then you can solve the differential equation you can do, okay. But I am not going into details, okay, but it is possible. You can also have CR buckling, that means you know Nx, Ny, no compressive forces, but you have a shear forces, and then the plate which is subjected to shear. So, the plate can also buckle under shear, and this is basically precursor to this plate is subjected to some kind of shear, something like this, and shear buckling, why it is important? Because he must have in in reinforced concrete design or say steel design, you have learned about tension field action, right? Tension field action, where you are designing the wave under against shear buckling, right? So, those things, theoretical stuff we can learn here, okay. How wave buckle under shear buckling, okay. So, there wave panel, that is what we provide stiffener, right, transverse stiffeners, longitudinal stiffener, all these things. So, shear buckling we will consider. So, this is basically the way we we consider the, you can see once again the analogy between the column and the plate. As far as buckling is concerned, not much difference, except there is another addition of a dimension, pi square A by L square, right. Here it is pi square d by b squares, pi square d by b square, and there is some 4, right, pi square, instead of pi square here the 4 is coming, pi square will be some around 9.80 whatever, right. So, but there will be some important thing if you go beyond buckling, okay, that is what. And like column, plate also shows similar behavior, I mean plate shows a little distinct behavior, that we will see. Now, this approach whatever we have done is based on the equilibrium, we have written down the equilibrium equation in the deformed configuration, and that is what we have solved an eigenvalue problem. This eigenvalue problem is a trigonometric eigenvalue problem to obtain the eigenvalues that will give you the buckling load eigenvector that will give the buckling mode shape, but you can also solve the same thing using energy approach, and you will see that the shear buckling we will consider using energy approach. So, let us pave the way to do the energy analysis for buckling, what in all the previous example we have followed. Okay. So, next class we are going to continue on that. Thank you very much for today's class.